What is the ultimate nature of matter in our universe? Throughout recorded history, the human mind has pondered this question. What are the smallest chemical building blocks that make up our world? For hundreds of years, chemists proposed models of this invisible particle and used them successfully. Yet only in the 1980s did humans finally see what had been predicted for so long: the atom.
I'm in a New York Hall of Science, a lively hands-on science museum in Queens. This quartz crystal, crystals like this, have been the object of admiration by people over thousands of years and of use. Sand, small quartz crystals is in glass and cement, and quartz crystals themselves have been used in radio receivers. But you know, when I, as a scientist, looked at this quartz crystal, what I want to see is the source of all of this perfection. I want to look into its innards. Why do these planes meet at this specific angle? What makes it so transparent? I want to take this crystal apart. I want to take it into smaller and smaller pieces, to apply to it microscopes of increasing magnification, and I can do that. And when I go to a magnification of the order of 100 million, I will see the indivisible components of this quartz, silicon and oxygen atoms. Actually, it wasn't as easy as I've made it out to be. It took us a good 2,000 years to get to see those atoms.
Using devices that range from the massive and complex to the small and simple, we have unlocked the atom and studied its structure. And we have learned of the incredible power held within it. Each day, this knowledge of the atom is applied in many ways. In medicine, signals from the atom are analyzed to produce vivid images of the body that can eliminate exploratory surgery. We can even examine mental activity in the brain. Nuclear reactors generate electricity for our homes and industry. In chemistry, the atom is central. Through our knowledge, we can predict and control chemical reactions. We can develop new alloys of metals, altering their properties to make them harder or more malleable, increasing their electrical conductivity or manipulating their strength. And a new generation of ceramics, superconducting and extremely strong, has been born. Our understanding of the atom enables us to create new drugs and paints, fertilizers and insecticides, cosmetics and fabrics. With our modern knowledge of the atom, we have developed new materials that have found their way into every aspect of our lives. Scientists use models of the atom constantly as they investigate the chemistry of the world around us. But where did the idea of the atom come from? It began with a Greek philosopher, Democritus. He proposed that all matter was made up of extremely tiny particles called atoms. Much later, in the 1800s, scientists revived the idea of the atom to explain events like this. By then, chemists were establishing that specific chemical reactions involved the combination of definite amounts of starting materials. They also noted that after the reaction was finished, the starting materials had yielded definite amounts of end products. Chemists like John Dalton used the idea of atoms to explain this, proposing that during reactions, atoms combined in predictable ways. Dalton's ideas were the beginning of our modern model of the atom in chemistry. In this model, the atom has 3 basic components and 2 basic regions. One of the components is called a proton and another the neutron. Together, the protons and neutrons make up the first region of the atomic world, the nucleus. The number of protons is what determines the identity of the atom. Protons and neutrons are held together by incredibly strong forces in the nucleus, which is actually extremely small compared to the total size of the atom. For example, this is the nucleus of a relatively simple atom, helium. The other region of the atomic world is occupied by the third component, electrons. This fuzzy cloud represents the space around the nucleus occupied by the electrons, called the electron cloud. The number of electrons in the cloud is equal to the number of protons in the nucleus. The electron cloud is 10,000 times larger than the nucleus. These glistening dots represent some of the possible positions of helium's 2 electrons as they move about the nucleus. Exactly how do the electrons move? Where are they at any given moment? No one knows the details of the electron's motion. What is known are the chances of finding it at any given point around the nucleus at a particular moment. Where the chances are high, the cloud is dark. Where they are low, the cloud looks lighter. Using indirect methods, scientists have established that atoms are all basically like this modern model. Throughout this century, scientists have imaged the atom with different X-ray techniques. Then in 1981, Gerd Benneck and Heinrich Rohrer of IBM in Switzerland invented a new microscope, producing brilliant images of single atoms.
Well, the first time I saw atoms, it was about 2 or 3 o'clock in the morning. Of course, I was doing most of my work at night because the instrument itself is extremely sensitive to vibration, so most of our experiments are done at night or on weekends. And it was about 2 or 3 o'clock in the morning, and I was staring at this image, and I started to notice this regular pattern appearing, which I knew had to be the positions of the atoms. And it just got better and better, and I was just elated. Eventually, just tears came to my eyes because I was so happy having worked on this day and night for so long.
Dr. Robert Hamers is at IBM's research division in Yorktown Heights. He has made significant contributions to the imaging capabilities of the Scanning Tunneling Microscope, STM for short.
We've been told ever since grade school science days that atoms are the ultimate building block of material. Now we can go in and we can actually look at those atoms. And so that's incredibly exciting to be able to do that.
The STM can produce both 2- and 3-dimensional images with color enhancement. Here, each small cone is an atom of silicon. These spheres are the atoms in gallium arsenide, a compound used in computer chips. And in this 2-dimensional image, we see atoms of aluminum and silicon.
Our present-day understanding of the atom is that it consists of a very small nucleus consisting of protons and neutrons, and this nucleus is surrounded by a diffuse cloud of electrons. And with the scanning tunneling microscope, what we're doing is mapping out the contours of these electron clouds.
The STM uses an extremely small needle to trace the shape of each atom's electron cloud, producing images like this. Images of the tiniest particles of the elements in the world around us. Images of an idea that began over 2,000 years ago. Images of the atom.
One of the unique features of the scanning tunneling microscope is that in addition to being one of the few instruments which can actually be used to observe individual atoms, it's also relatively inexpensive and provides a wealth of information. I think it's very likely that within 5 or 10 years, certainly every chemistry department in this country will probably have at least one scanning tunneling microscope.
The STM images were a dramatic confirmation of our modern view of the atom. But long before we could actually image individual atoms, a series of simple experiments had given us information about the components within the atoms. One of their most important characteristics is charge. Electrical charge holds the nucleus and the electron cloud together and determines the course of chemical reactions. How does electrical charge work in the atom? Series demonstrator, Don Showalter.
You notice anything different? Believe it or not, I did comb my hair this morning. What you're seeing is the result of electrical charge. This device now is producing an electrical charge that is being transmitted through my body to the hairs on my head. The electrical charge is what's making them stand on end. How is this happening?
So positive and negative charges attract in the atom, holding the electron cloud to the nucleus. How did we find out which components were positive and negative? An experimental device developed by William Crookes helped provide the answer. The Crookes tube. It produces a glowing stream of electrons. By using magnetic and electric fields, scientists were able to deflect the electrons. With this procedure, they were able to show that the electrons were negatively charged. In a similar experiment, another particle was discovered. It had a positive charge and was christened the proton. Much later, in a different experiment, a particle with no charge was found and named the neutron. In every atom, equal numbers of positively charged protons and negatively charged electrons balance each other. So the overall charge of an atom is zero. The atom is neutral. But the question of how positive and negative particles were arranged in the atom still needed resolution. The first clue came from an experiment performed by a physicist, Ernest Rutherford.
What you see here is a recreation of the Rutherford experiment. He used an element named polonium, which gives off positively charged particles. Now, he put the polonium into a lead box, something like this. It has a small opening in it. This is a lead barrier. It has a tiny hole in it that will allow only a thin beam of positively charged particles to pass through. There's an opening here, and then here is a very thin piece of gold foil. Surrounding the gold foil is this ring, which is specially coated with a material such that when a positively charged particle hits it, it gives off a flash of light. All right, now what do you think would happen if those positively charged particles hit the gold foil? Well, Rutherford thought they would pass right on through the foil and hit the ring about right here. Boy, was he in for a surprise. Now here's what actually happened.
Most of the particles passed right through the foil and hit the screen behind it, but not all of them. A few were deflected sideways, and about 1 in every 20,000 of them bounced off the foil back towards the source. Rutherford was astonished.
It was about as credible as if you'd fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
What was deflecting some of the particles? Rutherford calculated that each atom must have a nucleus, a center with a large mass and a positive charge concentrated into a small volume. The nucleus had to be massive enough to deflect the heavy particles bombarding it. And since the bombarding particles have a positive charge, the nucleus must have a positive charge to repel them. So once in a while, a particle would closely approach the nucleus and bounce back. But the majority of the particles passed right through the negatively charged electron clouds.
Rutherford's ingenious experiment gave us a simple model of the atom. A heavy nucleus with the positive charge and most of the mass, and around it light negative electrons. Then from quantum mechanics, another 20th century development of physics, we got a picture of how the electrons move. That was that cloud, and it's represented here in a model. The electrons don't move in orbits, like planets around the sun, but they do move. Sometimes they are near the nucleus, sometimes they are far, and we can, on the average, determine where they are. The electrons, though small, are moving throughout the whole volume of the atom, and when two atoms come together, That's actually what chemistry is all about, atoms coming together to give molecules. It is the electrons that feel each other first, not the nuclei. This is why the chemist is so interested in electrons. They make the difference, ultimately, between carbon, hydrogen, or lead.
What is it about the electrons that makes all the atoms of one substance different from all the atoms of another substance? The basic substances in the world around us each have a different number of electrons in their atoms. These electrons move about the nucleus in patterns that are different for each type of atom. For example, we have already seen one way that electrons may move around an atom, forming a cloud that looks like this. Here is a different cloud, shaped like an hourglass. The spherically shaped cloud is called an S cloud. The hourglass-shaped cloud is called a P cloud. What is the difference between the S and the P cloud? Energy. Each electron cloud has a certain amount of energy associated with it. This is called its energy state. The shape of the cloud depends on its energy state. If we were to diagram the energy levels of the S and the P cloud, they would look like this. The P cloud would be placed higher than the S cloud because the electrons in it have a greater amount of energy. And if energy is added to the atom, it is possible for the electron to change from one cloud shape to another. As it reverts to its initial state, the atom gives off energy signals. Chemists can use these signals from the electrons to distinguish between the atoms of many different substances, even when these atoms are present in very small numbers. How does this work? Environmental analysis is one example. In our environment, there are many trace elements. Some of them, like selenium, are harmful if too much is ingested, but are essential to human health in small amounts. For example, thousands of people in a region of China once suffered from a disease of the heart muscle. In fact, many died from it. Researchers analyzed the residents' surroundings. Using techniques that detect the energy signals from the electrons of different elements, they tested their water, their food, their air and their soil, looking for something out of the ordinary. Finally, they identified an abnormality in the soil. It was lacking in selenium, a vital trace element. Crops grown in the soil were deficient in selenium, so there wasn't enough in the residents' diet. This led to the heart disease. But once the inhabitants started taking selenium supplements, the disease was greatly reduced. Environmental analysts also use signals from the atom to detect elements that are harmful, even in very tiny amounts. Lead, for example. Lead can enter our environment in many ways. Because it was used as a gasoline additive, lead was present in our atmosphere above normal levels. Much of this lead settled in the soil of urban areas, where some of it still remains. From the soil, small amounts of lead may work their way into our water supply or our food. Our water may also pick it up from older pipes that were joined together with solder containing high amounts of lead. A most common source of lead poisoning is lead-based paint. Until a few years ago, most paint contained lead. If paint chips are accidentally ingested, their lead accumulates in the body. How do chemists use energy signals from the electrons to identify the atoms of substances like selenium and lead? One technique is emission spectroscopy. Dr. Robert Waters is head of atomic spectroscopy at the National Bureau of Standards.
Emission spectroscopy is an important part of analytical chemistry because it gives us the opportunity to find out what atoms are in a sample, and we can look at the possibility of a large number of different atoms being in the sample, and we can decide how much of each of these atoms are in a sample pretty much all at the same time.
The key to emission spectroscopy is color. When energy is added to an electron cloud, by heating it, for example, it gives off light that is a particular blend of colors. Each substance is different. Copper burns a bluish green, sodium, yellow. Lithium burns red. Barium is a pale green. These colors, or wavelengths of light, can be separated into a pattern called a spectrum. The spectrum for each particular kind of atom is different from that of every other atom.
Now, the element lead has a specific set of energy levels, and the wavelength of light that is given off by electrons, excited electrons from a lead atom, would have a specific value, so that we could tell that indeed we are looking at lead and not any other atom. And then the interesting thing then is that the number of lead atoms that are in this sample will cause a change in the intensity of this particular wavelength of light. Namely, the more intense that wavelength is that we see, the greater the number of lead atoms in the particular drinking water sample that we were interested in.
What happens to an electron when energy is added? How does it produce its unique spectrum? Here is an electron in an S cloud. Under normal circumstances, it maintains this energy level, neither gaining nor losing energy. This is called its ground state. When the electron in an S cloud is exposed to energy from an external source, for instance when light is shown on it, it may absorb energy and enter an excited state. If it absorbs an amount of energy exactly equal to the difference in energy between the two clouds, something unique occurs. The shape of the electron cloud changes from an S shape to a P shape. The electron has moved to a higher energy level. The change is instantaneous and complete. There are no stages in between the S shape and the P shape. But the electron tends to seek out the lowest energy level available. So once it absorbs energy and changes to the P cloud, the electron emits the energy as a particular color of light. In the process, it goes back to the ground state, the S cloud, a lower energy level. But as long as the energy source is present, the electron keeps flipping back and forth between the two cloud shapes. It keeps emitting the same pattern of color, the same energy signal, each time it goes from an excited state back to its ground state.
The energy difference is specific, in many cases, to a given atom. So that the light that is given off in the case of emission spectroscopy, the wavelength of light indicates what the energy difference was between the upper level and the lower level. And therefore, that wavelength or color of light gives us an indication as to what atom it was that we were looking at in the first place.
To review, understanding the makeup of the atom is important to understanding chemistry. In our modern model, the atom has three components: positively charged protons, neutrons with no charge, and negatively charged electrons. The electrons occupy a space called the electron cloud. Different electron clouds have different shapes depending upon their energy level. Two of the most common are the S cloud and the P cloud. When the S cloud changes to a P cloud, energy is absorbed. When the P cloud changes to an S, energy is given off. Scientists can use a technique called emission spectroscopy to analyze these energy signals and identify what types of atoms are present.
In another exhibit at the Hall of Science, we see the many different colors emitted by atoms in lamps. In this program, we've looked at the structure of the atom. We understand those marvelous electron clouds around the nucleus. And in an image that you saw at the beginning of the program, produced by a technique called scanning tunneling microscopy, we actually showed you an atom. Chemistry, like any human enterprise, operates on many levels. With partial, incomplete understanding, it's sometimes wrong. Incredibly, it's most of the time right. About 50 years before anyone ever knew about the atom, there was devised a remarkable chart summarizing all the properties of the atoms. That chart, called the periodic table, is the subject of our next program.